So, with this lecture, we start our discussion of cosmology. So, the idea we're going to use in this, this lecture and next one is the following. At the scales of the Sun system, we, in the space, see large empty spaces and very few bodies separated by large distances. But at the same time, if we go to larger scales, like 100 megaparsecs, then at these scales, universe looks rather homogeneous, like we have a very high precision, homogeneous and isotropic distribution of matter on these scales. Moreover, observational data show that distant galaxies are running in all directions, practically all galaxies that we see are running away from us. And in these lectures, we're going to discuss solutions of general theory of relativity which describe such a behavior. So, let us start with the discussion of the spacetimes which describe homogeneous and isotropic behavior. So, the most general four-dimensional metric tensor, which describes isotropic and homogeneous spatial sections, is as follows. So, the metric has this form, dt squared minus a squared of t times gamma ij, which depends only on spatial coordinates, dxi, dxj, where I and j run from 1 to 3. So here, dl squared, which is gamma ij of x, dxi, dxj, describes spatial sections that, and their size is changing in time according to the change in time of the scale factor a of t. Because of the homogeneity of spatial sections, all directions, all points in this space, and all directions from every point in this space should be equivalent. That is an idea of homogeneity. Hence, these three-dimensional spaces, they describe something which has constant curvature. And we're going to discuss that in greater detail. So let us discuss all sorts of possibilities for the homogeneous spatial sections. The metric tensor in space of constant curvature can be written in the following form. So we can write this metric in the following form, dr squared over 1 minus k r squared plus r squared d omega squared, where, as usual, d omega squared is the metric on the unit two-dimensional sphere, so it has this form, sine squared theta d phi squared. And there are three options for this parameter k. K can be equal to either -1, 0, or 1. So these three cases we're going to discuss now. Indeed, let us see that this space describes, for these three choices of k, this space describes homogeneous situation, which corresponds to constant curvature at the same time. So when k equals to 0, this is the first case, when k equals to 0, in this case we obtain dl squared, which is dr squared plus r squared d omega squared, which is nothing but a three-dimensional flat space written in spherical coordinates. Obviously, this is a homogeneous space. Every point of this space is equivalent to every other, and all directions from every point are equivalent. And obviously, this space corresponds to constant curvature situation. The curvature is 0. So the second case is when k equal to to 1. In this case, we obtain dl squared, which is dr squared divided by 1 minus k r squared oh, sorry, k. In this case, k is equal to 1, so here stands 1, plus r squared d omega squared. Now we can make a change of coordinates in this case. We can change to denote r as sine of chi, of some angle chi. Obviously, for this to be a space, r should run from 1 to -1. So this is a meaningful change. And then, if we make such a change in this metric, dl squared becomes familiar to us metric d chi squared plus sine squared chi d omega squared. We actually have encountered this metric in the lecture on Oppenheimer-Snyder collapse. This metric describes three-dimensional sphere. Indeed, let us see that. What is three-dimensional sphere? Three-dimensional sphere is the following surface, well, hypersurface. Three-dimensional unit sphere is this hypersurface embedded into four-dimensional space with the metric dw squared plus dx squared plus dy squared plus dz squared. So, how to see the relation between the metric on this sphere with the metric written here? Well, we just have to solve this equation. The solution of this equation is the following for Euclidean 4 vector. It is equivalent to cosine phi of phi, this phi, sine of phi multiplied by sine theta and cosine of phi, then sine of chi multiplied by sine of theta sine of phi, and finally sine of chi times cosine of theta. Well, obviously, if one square this plus square this plus square this plus square this, one will obtain that this is equal to 1. Then if one uses this in this metric, plugs into here, one obtains exactly this metric on the sphere. So, and why this is, well, obviously the sphere is a homogeneous space. In fact, this metric is, this surface, together with this metric, is invariant under SO4 rotations. Rotations in four-dimensional space. And every point of this, at the same time, every point of this space has a stabilizer, such a transformation which doesn't move it. For example, if W equals to 1, this is equal to 0, this 0, this 0, which solves this equation. So this point, it is quite a generic point. This point is stable under SO3 rotations in this part. So the space under discussion is the following homogeneous space, SO4 divided by SO3. So by the action of this group, we can move from any point of this space to any other point, and the action of this group doesn't change that point. So that's the reason it's a homogeneous space, and that explains that every point of this space is equivalent to every other, because it can be obtained by the action of this group. And every direction of this space is equivalent to every other direction. And obviously, this is a space of constant positive curvature. And that was the space of the constant zero curvature. So finally, we have to discuss this metric, dl squared for dr squared 1 minus k r squared plus r squared d omega squared for the case that k equals to -1. So in this case, obviously, we encounter this situation, dr squared 1 plus r squared plus r squared d omega squared. Now, if one will make a change that r is equal to hyperbolic sine, sinh, of chi, then this metric acquires the following form: d chi squared plus hyperbolic sine of chi squared d omega squared. What is this space? This space is actually Lobachevsky hyperplane, as we will see in a moment. So it's a space of constant negative curvature. So how to see that? The space of constant negative curvature is given by the following equation. So it's hypersurface defined by this equation in the four-dimensional Minkowski space of the following form, embedded into Minkowski space with the following metric. So how to see, before showing the relation between induced metric on this space with this metric, let us discuss why this space is homogeneous. First of all, one can straightforwardly see, rewriting this equation in the form that x squared plus y squared plus z squared is w squared minus 1. So for each value of w, greater than 1 or less than minus 1, we have a sphere, three-dimensional sphere. So the space looks, the picture of the, one can picture the space as follows. So it's a two-sheeted hyperboloid who has upper sheet starting with, this is w, and this is x, y, z, etc. And there is another sheet of this hyperboloid which starts with, this is 1, this is minus 1. And as w increases by absolute value from 1 or minus 1, the size of the sections increasing. So this basically, this picture corresponds to the case when we neglect z. So put z equals to 0. So this is the first sign that we're dealing with a space of constant curvature, but we are going to give a bit more explanations. One can see that this space has the obvious isometries, which is Lorentz group which contains Lorentz group SO31. So, and this group respects this equation, hence respects the space that we are discussing. And second thing, one can see that there is a point like W, X, Y, Z, such that 1, 0, 0, 0. This point solves this equation, so it lays on this space, inside this space, and the stabilizer of this point is rotation in this direction, SO3. SO3. Hence, the space that we are discussing is homogeneous space of the form SO31 divided by SO3. So every point of this space can be obtained from every other point by the action of this group, but generic point of this space has the stabilizer of this form. So this subgroup of this group doesn't move an arbitrary point in this space. So that's the reason it's homogeneous space. Every point of it is equivalent to every other, and every direction from every point of it is equivalent to every other direction. So that's a reason to expect this space to have a constant curvature. And finally, if one will solve this equation as follows: W, X, Y, Z equal to hyperbolic cosine of chi, hyperbolic sine of chi, times sine of theta, ordinary sine, times cosine of phi, times hyperbolic cosine, hyperbolic sine of chi, times sine of theta, times sine of phi, and finally hyperbolic sine of chi times ordinary cosine of theta. So obviously if one will square this, minus square of this, minus square of this, minus square of this, one will have this equation as a consequence of the fact that cosine squared plus sine squared is equal to 1, while hyperbolic cosine squared minus hyperbolic sine squared is equal to 1. So this does solve this equation. And at the same time, if one will make this, use this form of w, chi, and y, and z in this metric, plug it here, one will obtain this metric. Notice that this space is, it's a space, it's not space-time. Metric in it is spatial, purely spatial, while it is embedded into Minkowskian signature space-time. It is because this hyperbolic, while whole space has Minkowskian signature, this whole hyperboloid is space-like in this Minkowskian signature space-time.